Hello people! Today we are trying to recreate one of the most important experiments in science history, trying to demonstrate in our garage that quantum mechanics is real. This will employ quite a bit of vacuum technology. I'll also show you how to design this homemade electron gun necessary to make collimated beams of high energy electrons. And using it, we will try to rediscover the fundamental natures of wave and particles that sparked their quantum revolution of the last century. But first of all, let's see a little bit of historical background to understand where our experiment will be placed in history. At the end of the 19th century, matter was thought to be made of particles, while light consisted of electromagnetic waves propagating in space as described by Maxwell's equation. The new centuries, both of these beliefs fundamentally changed. First with light, when in 1901 Max Planck solved the famous black body radiation problem, while in 1923 Arthur Compton, while studying the scattering of X-ray by light element, indirectly proved that electromagnetic waves, or light, not only behaves as waves but also as discrete packets of energy, the newly called quanta. While on the matter side, electrons were discovered by J. Thomson in 1897. It was evident since the beginning that electrons are of corpuscular nature, fundamental indivisible particles, one separated from the other. In fact, their charge has been accurately measured by Millikan with his famous oil drop experiment in 1908, while Rutherford in 1920 discovered the proton. This way the model of the atom was almost complete, a nucleus of positive particles with negative particles electrons orbiting around. But all of this will soon change. In 1924, the PhD student Louis de Broglie published his thesis, where he proposed the revolutionary idea of particle-wave duality, where he suggested electrons could be described as a train of waves, moving together with group velocity proportional to the energy of the electron particle. Why is this so important if the wave nature of the electrons have never been observed before? Well, because this particle-wave duality is what made it possible for Erwin Schrödinger in 1925 to develop the now famous wave equation of motion for electrons, which sparked the beginning of quantum mechanics, explaining how electrons can be bonded inside atoms as waves, and not collapse into the nucleus while orbiting around, reshaping fundamentally our understanding of nature. So, how we prove de Broglie and Schrödinger are right, and that quantum computers are real and not a conspiracy from the lizard government? Well, we have to demonstrate that electrons also behave as waves, and not as particles that just bump into each other and do particle stuff. So, what is the most important difference of a wave? Well, that it can interact with itself and other waves. It can diffract and interfere. We should try to see if also electrons can diffract. And if they can, this means that particles can behave as waves. And so de Broglie was right. So this is the heart of this experiment, as it will be the electron source. The requirement for this experiment to work is to have a fine and well collimated electron beam. To do so, I've settled with this design, consisting of a single electrode assembly, unlike the other one we've built in the last video, where there were multiple electrodes to allow for focusing and changing of the beam diameter and angle. We then have a fermionic electron source, just a cut light bulb, and the whole cathode is placed at a negative potential to repel the electrons towards the target placed at ground potential. This design is also called long fine focus, where we make a beam that can stay collimated for very long distances, many tens of centimeters, and so the electrons are directly emitted and collimated as soon as they are outside of the cathode. The dimension of the negative electrode and the geometry is chosen so that the electrons are ejected from the cathode in a collimated manner. And to see how this works, we first need to see how a typical electron gun works. Normally we have a cathode and an anode, with an aperture placed in front of it. This creates a diverging electrostatic lens, as the electric field is interrupted due to the anode aperture, and as a consequence electrons are emitted in a diverging direction. To focus this diverging beam, other lenses are then stacked after the anode aperture. But with the long fine focus design I made for this gun, instead we have the cathode body at cathode potential that protrudes from the plane of the cathode where the filament is placed, creating an initial intrinsic converging effect onto the electrons that are repelled away from the cathode potential walls inward toward the center, and this effect, added to the natural diverging effect of the anode aperture, get cancelled out, leaving us with an almost perfectly collimated beam. This effect can be balanced by deciding how much the cathode body walls protrude outwards towards the anode, and what diameter it is. As the electron detection, we are simply going to use a conductive glass plate covered with a layer of phosphor from a CFL light bulb that emits light when hit by electrons. Now let's talk about the cathode. A similar experiment has been tried by my friend Big Bang Science on his YouTube channel, but he reported unsuccessful results. Between the causes, one was the background light coming from a tungsten filament source, as it was just too bright to see anything over the constant background from the light bulb. To avoid this problem, I'll use my secret recipe of oxide cathode thermionic emitter. This wet liquid, consisting of barium and strontium carbonate, when cast over the filament and dried, will make a very low work function material. This way we are gonna have much more electrons at much lower temperature. You can clearly see the difference it makes between a non-coated filament and one that is instead coated, both in current and in light background. To connect the cathode to the electrode body and make it easily replaceable if anything breaks, I used one of these alumina lamp holder that fit inside this tube, and then used a vacuum grade epoxy to seal everything. For this other side I simply used this groove machine into the aluminum piece and used a silicone o-ring tightly pressed inside by this glass insulator that separates the high voltage electrode from the anode. Finally, there is this plastic collar around that, using 4 screws, press the anode plate onto the vacuum chamber o-ring. The vacuum chamber is a simply metal body recycled from another machine that has 5 windows to see inside. And on the opposite window from the electron gun, I placed the phosphor screen to see the electron beam. The vacuum chamber connects to the pump from this bigger hole. First, we're gonna try the surface diffraction. If we shoot the electrons at a glazing angle, this means at a very shallow angle, almost parallel to the material surface, an interesting phenomenon should occur. This is the electrons take on their wave appearance and start to interfere within the first few layers of atom. This means that electrons get diffracted by the superficial atoms, and the new electron wave is emitted in all directions. What we actually see, if this is true, is the constructive interference between all the diffracted electron wave that only appears at a specific angle, which angle depends on the electron energy and the atom layer distances of the first few layers in the material. For this to work, we need a single crystal, that is a material with a very ordered structure and a definite orientation of the atoms. This is quite challenging to get, as everyday objects are usually made of polycrystalline materials, but I was able to find a suitable source as this piece of silicon, as this should come from a silicon wafer used to make chips, and this kind of silicon is grown using a particular method so that it is crystalline to control better the properties of the final chip semiconductor. Since we need a very shallow angle, I placed the silicon chip on this copper support that is almost parallel to the incoming electron beam, and made a pinhole in the copper so that only a very thin beam of electrons could pass through the hole and hit the crystal of silicon. It required quite a bit of attempts to get the right position and angles, but I finally could see some strange reflection that weren't in the same position as the main transmitted beam. I can't think of any other explanation for this peak beside that it's formed by the reflection of the electron's wave from the surface of the crystal, indicating at the wave nature of the electrons. Another indication of this being diffraction is the fact that by varying the energy of the electrons, by varying the high voltage potential of cathode, the position of this dot is changed, going towards the inside or outside. Unfortunately, I don't know in what way the random piece of silicon is oriented, so the pattern cannot be predicted. Let's now see my attempt at the second kind of experiment. This time we are going to try and see electron diffraction as it transmitted through a grating of atoms. This is the same phenomenon happening in lower X-ray diffraction I already showed you in a previous video. So this works by having a sample where the electrons are transmitted through, and if they are particles they will just penetrate if their energy is high enough, and the beam won't have any particularly interesting form. But if instead they behave as waves, each electron will have a certain probability of being scattered from an atom in the grating, and the diffracted waves will interfere and make a specific pattern that will take the image of a circular halo in the case if the grating is made of polycrystalline material. This is the same kind of experiment done by Thomson in 1927, the son of the discoverer of the electron, where he passed a collimative beam of electrons through a celluloid very thin film and observed this diffraction figure, where the main beam is transmitted, as we see in the center, while the circular halo of lower intensity around it is caused by the electrons behaving as waves, scattering inside of the target sample of celluloid. A better image obtained later shows some more details of the structure of the halo region, with zones of higher and lower intensity. But anyway, let's try it ourselves. The main problem here is the fact that we're using 10 kV electrons that get easily attenuated by very low amount of material. So we need an extra thin sample to make them pass through. I could get a graphite single layer, but they are very expensive. So I decided to try and use a nitrocellulose layer, made simply by placing a drop of the dissolved cellulose on the whole aperture and letting it dry. This should yield us with a very thin layer, few molecules thick, that electron can penetrate. I then placed the pinhole with the celluloid on the electron trajectory and looked at the transmitted beam. This required quite long exposure, as the intensity of the diffracted electrons is very low. But after some time I got this image, where we can clearly see the transmitted beam and the halo around it, of the same order of magnitude as the image collected by Thomson in 1927. The main difference is that he had a lot longer distance due to his vacuum chamber being bigger, so he could see a bigger image over longer distances. The circular halo is not present in the absence of cellulose. Also, we can see from these two areas that the intensity of the halo increases going towards the outside of the radius, and this is what it should actually be, as the electron diffraction has a circular pattern with higher fringes intensity and lower. And we can see actually in our photo these two regions with a higher pixel light than the middle intermediate region, where we actually should predict a lower electron intensity. So in conclusion, we have seen these two types of electron diffraction. The data are promising, but further experiments should be carried out to get higher quality images. The reflection setup would require a better sample holder to allow the choice of the incident angle, while for the transmission experiment other substances should be tried. Furthermore, both experiments are limited by the low amount of space between the sample diffracting and the detector. A higher length would allow for collection of a bigger image, and so allow to distinguish better the zone of higher and lower electron intensity. But still, I think this is a pretty good start. If you still have any question or opinion regarding the data or the experiment, remember to put them below. Bye!